And so you can see an example here. So for the reaction above, our oxidation was the magnesium, and so that's the anode. So you have your magnesium solid, a single line, your magnesium ions, which are aqueous, then your double line for your salt bridge, then your aluminum ions, your single line, and your aluminum electrode. Okay. Again, based on the cell, this is the electrode, right? The electrode, the solid that is connected to the wires to the voltmeter, and then these are the solutions. Okay, and the solutions are separated by the salt bridge. Right? So if all the components of a half reaction are ions, then none of them would dissolve into ions, and so they can't act as an electrode. So let's just say they cannot act as an electrode. So they have to have an inert conductor. So we need something that will conduct electricity but won't participate in the reaction. And typically we use platinum. Okay? PT is our inert electrode that is typically used. Alright, so let's look at this example here. So we have silver and iron. Again, my arrows are missing. Okay, so first we're going to find the cell reaction, and then we're going to answer the questions below. Alright, so let's first look and find what the cell reaction is going to be. So to determine that, we need to look up our values of E. Right? And so silver has a cell potential of, make sure you find the right silver plus 1 electron, has to match this equation here, of 0.8 volts. And then the iron, which is just a couple below it, is 0.77 volts. Again, these are both the reduction potentials. Okay? So again, for it to be a galvanic cell, it has to have a positive E. And so which of these can oxidize and still keep a positive E? Right? Exactly. So the iron has to be the one we flip. So we're going to flip the iron, so we iron plus 2, going to iron plus 3, and 1 electron, and that makes the E value then negative 0.77 volts. The silver will remain the same, and its E value stays at 0.8 volts. Now the electrons are already equal, so they cancel out. We add those halves together, and we get iron plus 2 plus a silver ion makes iron plus 3 and silver solid. And our cell potential would be these two here added together, which would be a positive 0.03 volts. Okay? So now, let's answer these questions. Does silver receive or lose electrons? Well, what does silver do? Silver has electrons on the left side, so that means it received electrons, right? And then iron, its electrons are on the product side, and so it lost electrons. Okay. How will electrons flow in the cell? Remember, electrons flow from the anode to the cathode. So the anode is where oxidation occurs, which is a loss of electrons. So they will flow from the iron, right, and to the silver. Right. What compartment does oxidation occur in? Always the anode. Right? Does this compartment function as the compartment is the iron compartment, and it is the anode. I jumped ahead. Right. What compartment does reduction occur in? That is the silver, and that is the cathode. So what is the electrode for the silver ion compartment? Well, since silver is a conductive metal, it is solid, right? We can use it as the electrode. What must the electrode be for the iron compartment? Well, since they're all ions, we have to use platinum. All right, so let's write our line notation, starting with our anode on the left. So our anode, we said, was our iron. So we have our platinum, a single line, forgot a solid, and then we have our iron solutions. Now since they're both solutions, they both go in before the salt bridge, and we just use a comma to separate them. Then we have our double line for our salt bridge, And then we have our silver solution of ions, and then we have our silver solid electrode, and that's our line notation. Okay? And that concludes our lesson for today.